as we've been talking about heat and temperature and phase changes and things like that, there comes a point when we actually have to put some data behind things. We have to do some calculations to make it mean something, aside from just saying, oh, it gets hotter, it gets colder, the particles spread out or get closer. We have to start calculating some things. Okay? Now, the amount of heat that moves from one place to another is actually deceptively hard to calculate. You'd think by now we have some kind of special heatometer, that we can point and take a heat measurement or something like that. How many joules of energy are being transmitted from one place to another? But actually, it's kind of tough. We're really good at measuring temperature. We've got thermometers and specialized temperature probes, thermocouples, all kinds of cool things that we can use to tell how hot or cold something is. But we're really bad at just measuring how much heat is absolutely moved from one place to another. Okay? Now, one way we can do it is by using the specific heat capacity of certain substances, which basically tells us how easy or hard it is to heat something up or cool something down. Now, the specific heat capacity involves a couple things. It involves the mass of that stuff we're heating up or cooling down. It involves the temperature change that actually happens when that stuff is heated up or cooled down. And finally, the amount of heat that is transferred from one place to another as it's heated up or cooled down. Okay? You can look up the specific heat capacity of all kinds of substances online, and you can also use a reference sheet like this that just gives you a whole bunch of stuff on what the specific heat capacities are. And that specific heat capacity basically tells you how much heat it takes for some amount of that stuff to get that much hotter or colder. Okay? This equation can help us do that. And so we're going to look at some examples of how we can use this equation and some algebra tricks to calculate the amount of heat that is transferred between stuff. So whether something loses this many joules of heat or absorbs this many joules of heat, or we can switch things around and look for the mass of some stuff or the temperature change of some stuff or even the specific heat capacity of an unknown substance using the amount of heat that is given or taken by something. Okay, in this first example, 35 grams of pure aluminum has its temperature increased by 200 degrees Celsius. How much heat, which is Q, measured in joules, big J, is absorbed by the aluminum to get it that hot, to get it hotter? Now, these variables that are next to each other are getting multiplied, but right now we're not really showing that. Technically, just by having variables next to each other, that implies multiplication, kind of like when you say 2x is 2 times x. But you can also see this other ways. Sometimes you'll see a dot to represent multiplication. Something like that. Or you'll see multiplication signs. Like that. These multiplication signs don't get used as much in higher level math because they start to get confused with x's, like a variable. So we just kind of try to avoid that. What I'm going to be using is parentheses. So having stuff in parentheses next to each other implies that they're going to get multiplied. Okay, just the same as the dot or the cross. This is just the way I like to do it. Okay, so if we want to figure out how much heat is being absorbed by this piece of aluminum, we need to take the mass times the specific heat capacity and then times the change in temperature that's going through. Okay, so Q is the missing variable we're trying to solve out. So Q equals, all right, our mass of our piece of aluminum was 35 grams. So there's my 35 grams right there. Okay, so that's my mass. Now the problem doesn't give me the specific heat capacity of aluminum, but I can look it up. Okay, so I've got a reference sheet. Looks kind of like this. Okay, that's got a whole list of stuff, and you can also look it up online, but this way we can kind of stay consistent. So I go and find aluminum, which has a specific heat capacity of 0.897 joules per gram degree Celsius. Okay, so I'm going to go ahead and just plug that in. since I know what the substance is, I mean, might as well. It's just a free number to, get closer to my answer. Okay. All right, so there's my specific heat capacity, 0.897 joules per gram degree Celsius. All right, and the temperature changed by 200 degrees Celsius. So that's my delta T. The delta is change in. The T, the big old T, is temperature. So if my specific heat capacity usually tells me it takes 0.897 joules of heat to get 1 gram of aluminum to change its temperature by 1 degree Celsius, well, in this case, I'm not using 1 gram, I'm using 35. And I'm not changing its temperature by 1 degree Celsius, I'm changing it by 200. So putting these into my calculation will help me to figure out how much heat it actually takes for 35 grams of aluminum to change its temperature by 200 degrees Celsius. Okay, so if I just take my mass times my specific heat capacity times my change in temperature, I should get my answer in joules of heat. Okay, so now how does that work out? Well, I mean, math-wise, you just take 35 times 0.897 times 200, but how do we get the unit that we want? Because right now we got a whole bunch of junk here. Okay. Well, remember that this specific heat capacity's unit is joules per gram per degree Celsius. Okay, you can kind of think of this like as it's getting multiplied and then divided by the grams in degrees Celsius. So if I take something that has a unit of per grams, that's being kind of divided by some number of grams, and multiply that by some number of grams, that will cancel out the units. It's like having a unit on top and a unit on the bottom. Bam, bam. Those go away. Anytime you have the same unit on the top and bottom of something be multiplied and divided together, they cancel out, just like unit conversion. Same case for our degree Celsius here. My degree Celsius is getting multiplied to this thing that has per degree Celsius. It's got degree Celsius on the bottom. It's getting divided. So that'll cancel that out too. Okay, something that's getting divided by degree Celsius times degree Celsius cancels out those degrees Celsius. So what unit do I have left? Joules. I just have joules of heat energy. So my answer is only going to have a unit of joules. Okay. Now, if that overwhelms you and you're like, oh, I just want to get through the math of it, please, that's okay. Okay. You can just kind of look for whatever answer you have left and know the unit that you need for that answer. But this is a way to ensure that you do the math correctly. I need to multiply my specific heat capacity by the mass and by the change in temperature to get my right answer. Okay, so if you go and plug this into a calculator, 35 times 0.897 times 200, we should get our amount of heat in joules. So let me plug this into a calculator. So 35 times 0.897 times 200 gets me 6,279 joules of heat. Let's make sure I wrote that correctly. Yes. Okay, and that is my answer. My aluminum absorbed 6,279 joules of heat. Okay, let's try a tougher example. Okay, in this case, if a lump of lead absorbs 4,500 joules of heat energy, causing the temperature to change by 50 degrees Celsius, what is the mass of the lead in grams? Okay, so let's plug in what we know. So in this case, they told us how much heat is getting absorbed by this thing. So we actually have Q in this case. So let's plug that in here. $4,500 joules is being absorbed by this piece of lead. Okay, now they told us what the material is made of. It's made of lead. So if I go find lead's specific heat capacity, there it is. It's 0.129 joules per gram degree Celsius. Okay. I'm going to stick that right up there so it's there for me. Okay. So I can plug in that specific heat capacity. That's C. 0.129 Celsius. Cool. Okay. Its temperature changed by 50 degrees Celsius. Okay, so what I'm missing is the mass. I want to know what the mass of this piece of lead is in grams. Okay, now like I said, most of the time practically in chemistry, we are trying to solve for the amount of heat that's being absorbed or released. But it is good to know how to use the heat energy to calculate something else, like in this case, the missing mass. Okay, this is just basically an algebra problem. I have to get my m, my mass, alone so I can figure out what it's equal to. Okay, so this is going to take a little bit more algebra than the last problem. I can't just plug everything in because these are on opposite sides of the equal sign. So let's see. If I want to get my mass alone, I'm going to have to divide and get rid of these two guys to get them away from it. So let's start with the specific heat capacity. So I'm going to divide both sides by 0.129 joules per gram degree Celsius. Okay? So if I divide both sides by the specific heat capacity, that will cancel out the specific heat capacity on the right side. That's great. So that's one less thing I have to worry about on the right side. I'm one step closer to getting my mass on its own. Now, this is going to work out to some new number. Okay? And I'm also going to be canceling out one of the units. Okay? So if I have joules on top here and joules on bottom here, those should cancel out. So that's cool. I'm on my way to getting the right units also. I'm down to just grams and degrees Celsius in there somewhere. Now this is something that always bothers me with units. So we are dividing by something that has units that are essentially being divided. This per grams and per degree Celsius is basically being divided from the joules unit here. So what happens when I take something that's being divided and divide it? It kind of undoes itself. If you think of something like 1 divided by 1/2. Okay? If you go and do this in a calculator, it equals 2. Okay? It kind of flips it back around. So if you think of it like 1 divided by 2, and I divide by 1 divided by 2, it kind of undoes the division. Okay? It's weird. It sort of flips it. So when you divide by something with a fraction like this, okay, whether it's an actual number or a unit, that stuff that would usually get divided is flipped and becomes multiplied. Okay? The same is true here. When you divide by units that are like this, they're like per gram degree Celsius, they get flipped to the top. So they become part of that answer. They become part of that new unit, is just grams and degrees Celsius. Okay? Now again, if this weirds you out and it makes it harder for you, then just look for the right units at the end of the problem. But this is where we're going to get kind of our next answer. Okay? So we're going to clean this up a little bit. 4,500 divided by 0.129 gives us 34,883.72. Okay. Now, what about our units? Well, we've canceled out our joules, so those are gone. Okay. Now, this grams and degrees Celsius are flipping up to the top. Okay, since we're dividing something that's divided, it undoes itself. It kind of goes back up on top. So this is going to be grams degrees Celsius as our unit here. And actually, I'm going to write this like this. My color coding is going to get a little wonky, so I'm just going to do a totally different color. Something like that. Okay. Now on the right side, what's left is our mass that we still don't know yet. And our temperature change in degrees Celsius. Whoa. Just flung my marker. Okay, well, I don't actually need that one. This one here. 50 degrees Celsius. Okay, so if I want to calculate the mass, I just need to divide both sides by this last thing that's kind of up against the mass here. Okay, so what does that do? Well, our 50 degrees Celsius on the right gets totally canceled out. So that's gone. Then on the left side, we're going to get a new number here, a new answer, and our degrees Celsius are going to go away. Since this is now up on top and this is now on bottom, degrees Celsius and degrees Celsius are going to cancel out. Okay? So what we'll be left with is just a unit of grams, which is the unit that we want for mass. Okay, so kind of a nasty journey, but we got there in the end. All right, so if we take 34,883.72 divided by 50, we should get our answer. That comes out to be about 697.67-ish. All right, and our unit is grams. All right, and that's our answer. Okay, now again, if I kind of lost you on the units, focus on the algebra, and then pick the unit that fits best afterwards. So to get our mass, we had to divide away the two things that were being multiplied to it, divide off the specific heat capacity, divide off the temperature change. That has to apply to both sides, so you divide off on both of those there. So we took the 4,500, divided by that specific heat capacity, divided by that temperature change, and what's left is the mass in grams. Okay, let's do another example. What is the change in temperature in degrees Celsius of a 2.5 gram piece of silver that absorbs 300 joules of heat energy? So again, this is a case where we're actually going to have the heat that we can plug into it, and we're going to have to calculate something else. This is going to require some algebra. So let's look at the algebra of that. Okay, so we are given that this piece of silver is absorbing 300 joules of heat. And this time we're given the mass. We know that it's 2.5 grams. Now the problem doesn't tell me what the specific heat capacity of the stuff is, but it does tell me that we're dealing with silver. And I can look up specific heat capacity of silver on my sheet right here. So I'm going to find silver. It's right there. 0.235 joules per gram degree Celsius. So I'm going to plug that in for my specific heat capacity. Okay, so the thing I'm missing is the temperature change. How much is the temperature increasing or decreasing by? Okay. So in order to figure out what the change in temperature is going to be, I need to get this delta T alone. I need to get this other junk away from it. Okay? So kind of like the last problem, I'm going to need to divide these away to undo the multiplying that I have on the right side here. Okay? So, like the last problem, if I want to get rid of this 2.5 grams that's multiplied to all this stuff, I do the opposite by dividing on both sides. But having to write it dividing on both sides sometimes takes a couple extra seconds or sometimes a minute. So if you want to do it a little bit of a faster way, this is the way I do it. If I know something like this mass is going to get divided, I just pitch it over to the bottom over on the other side. It's kind of like whatever's on the top is now going to be on the bottom of the other side. If I had something on the bottom over here and I needed to multiply it, it would do the opposite and go to the top of the other side. Okay? So in this case, whatever's on the top over here is going on the bottom of the other side. Okay? And I'm going to get rid of it over here. Okay? So I still end up with the same kind of result. I'm going to still have this stuff divided by this stuff. I just don't go through and I have to do the whole bar there and then write 2.5 underneath it and then cancel this out. It gives me a little extra room and it takes a little less time. Not a huge shortcut, but I like it. So we're canceling out our 2.5 grams on the right side by dividing it over on the other side of the equal sign. Okay, in this case, none of our units are canceling. They're all still there. So I'm just going to divide 300 by 2.5 and see what my new answer is. So where is my calculator? So 300 divided by 2.5 gives me 120. Okay, and the unit is going to be joules per gram. Okay, interesting. All right, so let me write out the rest of what we have left. Our mass is gone. We still have our specific heat capacity and our change in temperature. Okay, so if I want to get my change in temperature alone, I've got to do another division. I've got to divide this from both sides, or we take the shortcut and we divide this over to the bottom of the other side of the equal sign. I don't really worry about the right side. I just say, it's gone. So I get rid of it over on the right side so that it can be divided over on the left side. Okay, So then what happens to our units? Okay, well, whatever I have on the top and bottom on the right side can cancel out. Joules over joules, out. Per grams over per grams, out. So the thing that's left is this degrees Celsius. It's like divided by per degree Celsius, divided by degree Celsius. It's that case of we're dividing by something that's already getting divided. It undoes it, it flips it, okay? So it's gonna end up on the top with our number, okay? So whatever this calculates to be, it's gonna have a unit of degrees Celsius. It flips back up to the top. So I'm going to take 120 divided by 0.235. 120 divided by 0.235, and I get about 510.64-ish. And the last remaining unit is degrees Celsius, which is great because I'm looking for the change in temperature. I should have something with a unit of degrees Celsius. Okay, so that's my answer. My silver changes its temperature by 510.64 degrees Celsius. Okay, that's my delta T. Now, something that this doesn't tell us is whether that is an increase in temperature or a decrease in temperature. This is just the temperature change at the moment. So like, how do I know that it's getting 510.64 degrees Celsius hotter, or if it's getting 510.64 degrees Celsius colder? Well, some of it we can figure out from the context of the problem. So in this case, we're told that our silver absorbs 300 joules of energy. So if it's taking heat in, it should get hotter. So whatever temperature that silver started at, it's now 510-ish degrees hotter. To show in our math, in our calculations, whether something is absorbing heat or releasing heat, or whether something is getting hotter or colder, is by using positive or negative signs. So up till now, all our examples have had heat being absorbed, heat's being taken in, things are therefore getting hotter. Okay? To show that, our Q value, our heat, is going to be positive. Okay? Since we're taking energy in, our energy is increasing. All right? So it comes out as a positive number. As the temperature change is getting higher and higher, we show that as a positive number, okay? As stuff is getting hotter and hotter. Now, if something loses heat or releases heat, our Q value is going to be negative to show that our amount of energy is going down. We are losing heat from the stuff we're worried about. And therefore, since our stuff is getting colder, our change in temperature is going to be a negative number, okay? So that way, if we have a change in temperature of 20 degrees Celsius, we can show that that means we're getting 20 degrees hotter with a positive 20 degrees Celsius. And we can show that it's getting 20 degrees colder by writing it as negative 20 degrees Celsius. Okay? So, if heat's going in, heat's getting absorbed by something, right, that is positive, and the temperature change is positive. These go together, okay? Don't make one of these positive and the other negative, otherwise you're going to end up with like a negative mass or a negative specific heat capacity, and it's not going to turn out well. And same thing for here too. If one of these is negative, so is the other. Negative heat means a negative change in temperature. Make sure to keep those carefully, together like that.